In the previous lecture, we discussed about the convolution operation and the impulse response of discrete LTI system, and we illustrated how the convolution operation is performed with an example of a discrete time system and taking discrete signal as an input and producing an output, which is the convolution between the input and the impulse response of the system. Okay, so basically what we did was we took and if we say that the input to a discrete system is delta of n, which is a unit impulse function, then the output that we get is called as the impulse response of the system, which we denote as h of n. And for an LTI system, if we know the impulse response of the system, that is, if we know h of n, then we know everything about the system. That means h of n characterizes the LTI system completely. So therefore, if we know what is the output of the discrete LTI system for an input which is a unit impulse, then we can find the output of the LTI system for any arbitrary input signal. So using this characterization of the system, that is its impulse response h of n, we can find the output of the system to any arbitrary input x of n. So the output that we get here, we'll call it as y of n, and that is nothing but the input x of n convolved with the impulse response h of n. And I illustrated in the previous lecture as to what this convolution operation represents and how to perform this convolution. Okay, this was illustrated in detail in the previous lecture. So just to summarize this, we're just trying to recap what we did in the previous lecture. So h of n denotes the impulse response of the system, and the star that is here, okay, the star operator here denotes the convolution operation. So star denotes convolution operation. Okay, in today's lecture we are going to extend this idea to continuous time systems. So rather than using discrete time systems where the argument is an integer which takes on only integer values, we are going to now extend this idea of convolution and impulse response to the continuous time case, and we will show that the continuous time output in fact happens to be the convolution between the continuous time input and the continuous impulse response of the system. Okay, we're not going to prove that, but we will use that relationship. So the same idea applies to a continuous time system as well, and we had illustrated this in detail and discussed in detail in the previous lecture as to how to perform this convolution operation. So let us now look at the continuous time case. So basically what we are saying now is, if we have an LTI system in continuous time, okay, LTI system, and if the input to this system is a continuous unit impulse function, which we denote as delta of t now. So previously it is discrete, so we denote delta of n in square brackets. That's the standard notation for discrete, and for the continuous case we use round brackets, and the variable, the independent variable, is time, which can take on even non-integer values as compared to the independent variable of the discrete case, which takes on only integer values. So time t can take on non-integer values as well in the case of continuous time. Okay, so the response of an LTI system when the input is a continuous time unit impulse function is the impulse response of the system, which we denote as in the notation for discrete case, we call it as h of t. Instead of h of n in square brackets, it is now h of t in rounded brackets. So this h of t is nothing but the impulse response of the continuous time system. So that's called as the impulse response. Now again, as we know the impulse response of the LTI system, that impulse response characterizes the LTI system completely. That means it tells us everything about the LTI system. So with that information about the impulse response, we can now find the output of the system to any arbitrary input x of t. So if we take any x of t, then the corresponding output of the system y of t is the convolution between x of t and the impulse response h of t. Okay, and just as we had expanded this convolution operation in the discrete case, so how did we write that? Y of n equals x of n convolved with h of n, and that is equal to, it's called as the convolutional sum, right? So that is x of k times h of n minus k for k equals minus infinity to infinity. Now that's the representation of the convolution operation. Now we have to take this to the continuous time case. So in the continuous time case, this summation will get replaced by integration, and these variables would get replaced by continuous time variables rather than being integers, right? So in the continuous case, again the star here denotes the convolution operation. So y of t, in this case y of t equals the convolution between the input x of t and the impulse response h of t of the system, which is equal to, in the place of summation we have integration now because it is continuous now, and the variables, instead of x of k, we'll call it as x of tau, because tau is k is taking integer values. What we have now, tau, which takes on continuous values. So x of tau into h of t minus tau d tau. Okay, that would be our values, or the convolution sum in the continuous time, or we call it as the convolution integral, and tau takes on the values from minus infinity to infinity. So that's the convolution sum or superposition sum represented in the continuous time domain. So this integral that we have here is called as the convolution integral or the superposition integral. Similar to what we had previously, we call this in the discrete case, we call this as the convolution sum or the superposition sum, because it is a summation which over integer values of this variable. But now we have integration over continuous values of the variable, so it is called as the convolution integral or the superposition integral. So this integral is called as the convolution integral or the superposition integral. Okay, and this arises due to the consequence of being able to represent any signal x of t in terms of delta of t, right? Just as we could represent any input signal x of n as a summation of shifted and scaled delta functions in the discrete time. Similarly, a continuous time signal, any arbitrary continuous time signal, can be represented as an integral of shifted and scaled delta functions, right? So for an LTI system, if we know h of t, which is the response to a unit impulse, then the response to shifted and scaled unit impulse would be a shifted and scaled version of h of t. So that brings us to this convolution sum, as we discussed in detail in the previous lecture for the discrete time case. Okay, the similar concepts apply to the continuous time case as well. So basically, this arises from the fact that any arbitrary signal can be represented as a sum of shifted and scaled versions of the unit impulse functions, and therefore the output to an LTI system, given the knowledge of its impulse response, is basically going to be the convolution sum, which is summation x of k times h of n minus k over all k. Okay, that is k for all the possible values of k. Okay, in general we write it as k minus infinity to plus infinity, right? So let me write that specifically, k equals minus infinity to infinity here. Similarly, in the continuous time case, the continuous time signal x of t can be represented as a summation or a superposition of shifted and scaled impulse functions, that is x of tau times delta of t minus tau, for all possible values of tau, right? So that's the representation of any arbitrary signal x of t in terms of the delta function. So correspondingly, the output of an LTI system, given the knowledge of the impulse response of the system, is x of tau times h of t minus tau d tau for all values of tau, that is tau equals minus infinity to plus infinity. Okay, that is called as the convolution integral. I'm just recapping these things. This is again an idea that we developed a few lectures back when we represented any discrete signal or a continuous signal in terms of the impulse function as shifted and scaled impulse functions, right? So for an LTI system, when the impulse response is known, then the response of the system to a shifted and scaled impulse is the shifted and scaled impulse response of the system, right? So therefore we can represent the output of the system to any arbitrary input x of n as the convolution sum or the convolution integral, depending on whether it's a discrete time system or a continuous time system. Okay, so we have now the equation for the convolution sum, that is basically x of t convolved with h of t, and let me put that in a square here, and because that's an important relationship here, that's an important representation. And right, I need to put that properly. Okay, so that's called as the convolution sum or superposition convolution integral or superposition integral in the continuous time case. Okay, now we'll take an example of an impulse response of a continuous time system, and then we'll see how to compute the output of the system, and in the process we will see how to perform convolution for the continuous time case. Okay, just as we did the convolution operation illustrated in detail in the previous lecture for the discrete case, today we are going to see how to perform the convolution operation for the continuous time case. So we are going to take h of t, the impulse response, as an example case for this, and we'll take x of t as some input signal, and then we'll try to perform the convolution operation and calculate what is y of t. So that way we will see how to find y of t and also see how to perform convolution in the continuous time domain. Okay, so that will be the focus of this particular lecture. So let us take this example where we consider a system which has an impulse response given by h of t equals u of t. U of t is the unit step function. That means when the input is a unit impulse function, okay, which is a delta function, the output h of t is a step function. What this equation means is basically if we have a system which I'm going to mark as this, okay, it's an LTI system, and if we give an input to the system which is delta of t, which is a unit impulse signal, the output that we get is h of t equals the unit step function u of t. Or if we had to plot this, basically what that means is when the input is a delta function, which is okay, which is a unit impulse function, which is delta function. So that's t, that's delta of t, right? And the output that we get from this system, for example, okay, is a unit step function. That means the output of the system when the input is a unit impulse is going to be something like this. So the output is a unit step. Okay, that's what this relationship means. When we give an input which is an impulse, the output is a step function which is constant for all, a constant value of 1 for all t greater than or equal to 0. That's what it means, right? So that's t, and that is u of t, which has a value of 1 for all t greater than or equal to 0, right? So for t less than 0, it is 0. So that is the impulse response of the system. And given that we know the impulse response of the system, we want to find the output of the system to some input x of t. So find the output of the same system when the input x of t equals e power minus at for t greater than or equal to 0 and 0 for t less than 0, and given that the value a, which is the exponent here, is positive, a greater than 0. Okay, this is the condition given. So now we are told that the system produces an output u of t when the input is delta of t, and using this information we are asked to find the output of the system y of t when the input is given by this x of t. Now basically what it means is this x of t is having this value e power minus at only for t greater than or equal to 0, and for t less than 0 it is 0. That means on the left hand side of the y-axis it is 0. Okay, that's what this is implying. Okay, now we can write this x of t in simple terms by using u of t, because rather than writing it as two values for different ranges of t, we can combine these two by using the information of our knowledge of u of t, that u of t is equal to 1 when t is greater than or equal to 0 and 0 when t less than 0. So we can write this x of t. Okay, so we can write this x of t as e power minus at times u of t. Now this u of t is equal to 1 for t greater than 0 or greater than or equal to 0. So that means when t is greater than or equal to 0, this term gets multiplied with 1, we get e power minus at, and when t is less than 0, this e power minus at gets multiplied with 0, it becomes 0, right? So rather than writing it as two different conditions, we can simply multiply it with u of t and then specify our range for a. Okay, a is greater than 0. Okay, now we are asked to find what is the output of the system when the input is this particular x of t, given that the impulse response of the system h of t is a unit step function which is u of t, denoted as u of t. So the output is based on our convolution integral y of t, because we are talking about LTI systems now. Y of t is x of t convolved with h of t, and again what is this condition a greater than 0 telling us? It's basically saying that a takes on only positive numbers. That means this e power minus at for all it will be a decaying exponent for all values of a specified in this range. Okay, so I'll just illustrate that with a plot as well, and then we will perform the convolution operation with the help of figures and try to understand exactly what is happening here. Okay, first of all, I've shown here what our x of t looks like. Okay, x of t is basically these plots for different values of a. Okay, and a is positive. A is positive. That means e power minus at will be e power minus something all for all values of t, and therefore all of these are decaying exponentials. So when as the value of a increases more and more, that it increases, we see that the exponent this exponential signal is decaying faster. So for a 0.5 it is decaying slowly, for a equal to 1 it is decaying faster, and for a equal to 2 it is decaying even faster, it is reducing even faster, right? So basically as a increases, the rate of decay of the signal is increasing. Now restricting this to a to be positive is basically signifying that all the this x of t is a decaying exponential for any value of a, because if a becomes negative, e power minus into minus a will become e power plus a, that will become a growing exponential. Okay, so we are basically restricting this x of t to be a decaying exponential. So that is what this a greater than 0 means. Okay, so for any value of a, it's going to be some decaying exponential which looks like one of these figures. Okay, the higher the value of a, the faster is the rate of decay for this exponential signal. And the h of t, okay, which is the impulse response, is what we have depicted over here. And now we want to compute y of t, which is the convolutional integral, which is given as integral x of tau, okay, into h of t minus tau d tau, for tau equals minus infinity to infinity. Now we are going to use some of the concepts that we have discussed earlier to depict this h of t minus tau. Okay, first of all we'll depict what is h of tau, and then we will make it h of minus tau, which is a reversed version of h of tau, and then we'll add this plus t and get shifted and reversed versions of h of tau. Okay, h of t, basically h of t. So that way we will see for what combinations of this h of t minus tau does this product which is inside this integral is non-zero, because we are interested only in the range where this product of x of tau and h of t minus tau is non-zero. For all other values we are not interested, because the product becomes 0 and therefore the integral becomes 0. So we want to find the range of values of t for which this product becomes non-zero. So we will illustrate that with the help of diagrams. So to find this output, we first want to represent our x of t as x of tau. Basically, we just change t as tau. Okay, just put the variable as tau. So rather than having x-axis as t, we'll just make it as tau. Okay, some other it's like a dummy variable, for example. Okay, and we'll represent this x of t as x of tau now. So we're going to have tau on the x-axis and x of tau on the y-axis. And as we have seen in these plots here, this signal x of t is basically a decaying exponential which is decaying at some rate for some value of a. Okay, so we'll have this as a decaying exponential which looks something like this. Okay, so that's a decaying exponential which we have denoted as x of tau. And the impulse response that we have for the system is a unit step function. H of t is u of t, which is like this. So we will plot that also over here. So the impulse response is going to be something like this. So it is 1 for t greater than or equal to 0. So that's our h of t. So that's t, and that's h of t, which is equal to u of t. Okay, now we want to find, as we see in our integral here, in the convolution integral, we want to find h of t minus tau. So first of all, we will write it as h of tau rather than h of t. So we will change this variable as h of tau. So I'm just going to erase that. This is just a change of variable. Okay, so h of tau, which is basically equal to u of tau. Okay, so in that case our x-axis value here is also tau. We're just changing some variables. It's the same thing. Okay, so now we have h of tau. Next, what we want to do is, in this integral, we want h of minus tau, because this tau is minus here, so that means it's a time reversed version of h of tau. So we'll have h of minus tau, so that will be tau and h of minus tau. And basically, as we have discussed previously, time reversal is basically rotating this x-axis by 180 degrees. So it's like looking at this signal from behind the screen. So that will give us h of minus tau to be like this. Okay, so that's our h of minus tau. And because it's a unit step function, the value is 1 for t greater than, or tau greater than or equal to 0 when it is h of tau. And for h of minus tau, now this is equal to 1 for tau less than or equal to 0. Now the next step we have to do is we need to shift it by some amount t. So h of minus tau plus t. So when we are shifting it by plus some amount, it is shifting to the left when this amount of shift t is positive, right? So normally when it is plus, it is shifting to the left, and when it is minus, it is shifting to the right. But because the time axis is already reversed, h of minus tau plus t will be shifted to the right when it is plus and shifted to the left when it is minus. Okay, so basically we are going to have here the shifted versions of this h. This is tau and h of minus tau plus t. Okay, and we'll do it for different values of t. So when t is positive, when t is greater than 0, this is h of minus t plus minus tau plus t, and since t is positive, it remains plus t. Okay, plus of plus some number, so it h of minus tau plus t, and plus usually means left shift, but in this case, because the time axis is already reversed, it's going to be a right shifted version of what we have at minus tau. So what we have here, this is going to be shifted to the right by a certain amount. So for t greater than 0, we'll have it like this. So it will be shifted by some amount depending on the value of t. So whatever is the value of this t here, when t is positive, it will get shifted by an amount t. Okay, and similarly, when t is less than 0, this will become h of minus t minus tau minus t when t is negative, right? So we'll put that case for t less than 0, we'll have tau and h of minus tau plus t. So basically, when t is less than 0, this will become h of minus tau minus t, right? And whenever this shift is a minus here, that means usually a right shift, but because the time axis is already reversed, that will be now a left shift. So basically h of minus tau minus t when t is less than 0, because t is negative now, so it becomes minus t. So that will be a left shifted version of h of minus tau. That means it is this thing shifted to the left by some value t. So we'll have it something like this. It will come from here, and it is shifted to the left by some t. Okay, so it will go to minus t here, right? Let me Okay, it is shifted to the left by t, so that means it will end up at some minus t over here. So what we have here is we have the shifted versions of the impulse response. So that's our original impulse response, and that's the time reversed version of the impulse response, and that's the time reversed and shifted version of the impulse response. And we have the shift depending on two particular values of t, for t positive and for t negative. And what we notice here is that when t is less than 0, for all values of t less than 0, there is no overlap between x of tau and h of minus tau plus t. Between this figure signal at the top and this signal at the bottom, there is no overlap. When we multiply these two, it's going to be 0, because x of tau is 0 for tau less than 0, and this one is non-zero only for tau less than 0. So whatever is here, it gets multiplied by 0 over here, so that becomes 0. And for all of these values, for all tau greater than 0, this particular signal is 0. So 0 into anything is 0. So basically this convolution sum that we have here, this product inside this integral, is going to be 0 for all tau which is less than 0. Okay, for all tau less than 0, that integral is going to be 0. So from minus infinity to 0, this entire integral is going to this product inside this integral is going to be 0. So we are interested only in this product for all positive values of tau. That is, this integral will be non-zero only in positive values of tau, that is from 0 to infinity. Okay, so that is what we are trying to depict here. So basically our product of x of tau and h of minus tau plus t, okay, which is h of t minus tau, right, minus tau plus t, that product is non-zero only for tau t greater than 0, right? Okay, when t is positive. For all other values of t, it is going to be 0. So basically what we are saying is, when we multiply x of tau with h of minus t plus tau, we see that they have an overlap only from 0 to t. For all other values, there is no overlap, which is giving us a non-zero value. So what we are basically seeing here is that x of tau and h of minus tau plus t, they have a non-zero overlap only in the interval 0 to t for tau. Okay, for any value outside this interval, when tau takes on any value other than being between 0 and t, we see that x of tau into this h of minus tau plus t is going to be 0, because outside this region here, x of tau is non-zero, but h of minus tau plus t is 0. To the left of 0, while h of minus tau plus t is non-zero for certain values, but x of tau is 0 for all values of tau less than 0. So we see that this product x of tau into h of t minus tau, which is in our convolution integral, is non-zero only for the range of tau between 0 and t, only between 0 and t. So that's our t over here. Okay, this point of time. So only for 0 and t, this is non-zero. That means the convolution integral, which is our y, denoting our y of t, equals integral x of tau into h of t minus tau d tau. This product inside this integral, which I will mark here, okay, this product over here is non-zero only when tau is in the range of 0 to t. Okay, only when it is between 0 and t. So we are interested in this integral only for the range 0 to t. And in that interval 0 to t, the value of h of t minus tau is equal to 1. Okay, this height is equal to 1 over here, right? This height is 1 here. Okay, so this height here is basically equal to 1 for 0 to t. So x of tau into h of t minus tau is basically x of tau when we are in this range 0 to t. So in other words, this product is basically equal to, or we can write that as x of tau times, let me write that x properly, x of tau times h of t minus tau is equal to x of tau when tau is between 0 and t, that is 0 less than tau. Okay, I'll need to rewrite that so it becomes clear. Okay, let me do that, just give me a moment. That is basically what we're saying is this product here, x of tau into h of t minus tau, is equal to x of tau because h of t minus tau is 1 in that range. Okay, and it is only in that interval, which I've shown here in this blue box, that both are non-zero. Outside that interval, either to the right of t or to the left of 0, one of those two elements is going to be 0, so therefore the product will be 0. So x of tau into h of t minus tau is equal to x of tau only in the range of tau for 0 to t, and for all other values of tau it is equal to 0. And what is x of tau? We have taken x of t as e power minus at u of t, right? So it's basically e power minus at in that range. So in other words, this product here is equal to, we can rewrite that in terms of the definition of x of t. So therefore we can write x of tau into h of t minus tau is equal to e power minus at for tau between 0 and t, and 0 for all other values of tau. Okay, so we have this notation for this product. Now we need to find the output y of t. So y of t is integral x of tau into h of t minus tau d tau for tau minus infinity to infinity. But since this product here is non-zero and having this value only in this range 0 to t, and for all other values of tau it is 0, so we are interested in this integral only in this range 0 to t. So therefore we'll write this as integral 0 to t, and in this range 0 to t, this product here is equal to e power minus at. So it's e power minus at it's e power minus a tau though, okay, because we are writing it in terms of tau. So even here I have to make that correction. So it's e power minus a tau d tau, right? So here also it should be tau here, okay, not t. Okay, e power minus a tau when tau is between 0 to t and 0 otherwise. Okay, now we have just substituted the value of this product where it is non-zero, and we are integrating only in that interval where it is non-zero. So this is a simple integral now, e power x. Okay, e power x, what is integral e power x or e power ax? It's 1 by a e power x, right? So we just have to integrate this and apply the limits. So integral of e power minus a tau is e power minus a tau divided by minus a, that is. divided by minus a, and then we apply the limits of integral, which is 0 to t. So now we can write that as minus 1 by a e power minus a tau in the range 0 to t. So that will become minus 1 upon a times, in place of tau, we are going to put the limit t, which is e power minus a t minus e power 0. So that will give us minus 1 by a into e power minus a t minus e power 0 is 1. Okay, now we can multiply it with this minus 1, and so we can write that as 1 by a into 1 minus e power minus a t. Okay, so that's the response of the system y of t when the input is the x of t that we have chosen, which is e power minus a t into u of t. Okay, so we have seen how to compute the impulse response of a system and how to perform the convolution operation. So basically what we have to do is we have to check the region of interest where the integral inside, where the product inside the convolution integral is non-zero, and we integrate only in that limit, and we find out what is the value of this product in the range of tau where this product is non-zero. Okay, so we have to kind of visualize the signals, and then based on the visualization of the impulse response as well as the signal, and we need to be clear about how to perform the time reversal and time shift for various values or combinations of time, and then identify the region of interest, okay, where both the functions will be non-zero, so that their product will be non-zero, and from that we will be able to determine what is the range of integral at which that product is non-zero, and what is the value there in that range. Okay, and then we can integrate and find the response of the system to that particular input signal x of t. Okay, so what we see here is that the response of the system y of t when the input is x of t is 1 by a into 1 minus e power minus a t, and that is valid only for all the values of t which is greater than 0, right? And finally, as a last piece of expressing this result, since our input signal x of t is defined only for positive values of t, right? We have seen here x of t is defined only for positive values of time. So that's what we have seen here, right? That's why we multiplied this with u of t, okay? And if we did not multiply it with u of t, we have to express it in these two forms, that for t greater than 0 it is having one value, and for t less than 0 it is 0. So since we have our input signal x of t defined only for positive values of time, therefore our output y of t is also defined for positive values of time. Okay, so what we are going to do is we're going to finally represent this y of t as this, and to say that this is valid only for t greater than or equal to 0, we have to be very clear about our representation of our signals. Okay, this is valid only for t greater than 0, right? So therefore we can write that very concisely as y of t equals 1 by a into 1 minus e power minus a t, and to say that it is valid only for t greater than 0, we multiply it with u of t. Okay, it's greater than or equal to 0, but at t equal to 0 in the continuous case it's a discontinuity, right? Because we can't say that t equal whether t at t equal to 0 whether u of t is taking the value of 0 or 1. Okay, it can't be both, so we just say it is having this value, this non-zero value for t greater than 0, or instead of saying t greater than 0 as we have said here, okay, for t greater than 0, we have just multiplied it with u of t. Okay, so that's the way of representing it. So we need to specify the time interval for the time range in which a particular signal is represented. Okay, so this y of t is given by this function only for t greater than 0, so we multiply it with u of t. So if we represent any signal, okay, whether it's the input signal or the output signal or the impulse response of the system, we need to represent the time range in which a particular expression is valid. Okay, so, and because it may be valid only for certain time ranges, as in this example, and outside that time range it will be 0. Okay, so we will have to be very specific and clear about representing our signals, because we need to not just give the expression but also specify the time interval in that in which that expression is valid. Okay, because outside the time interval it may have a different value, so we need to specify the signal in each of the time ranges. Okay, so basically we have seen today in this lecture the process of performing convolution in the continuous time domain, and just as we did in the discrete time domain, we had a similar expression. So to summarize this, let me write that summary. Okay, in the continuous in the discrete case, okay, in discrete time, now we represented the convolution sum y of n as x of n convolved with our impulse response h of n, which is summation x of k, that is in square brackets, x of k times h of n minus k for k equals minus infinity to infinity. And in the continuous time case, we will now write h of y of t as the convolution between the input x of t and the impulse response h of t. And now the convolution sum becomes the convolution integral, which we denote as integral x of tau into h of t minus tau d tau for tau ranging from minus infinity to infinity. Okay, and you see they are quite similar in terms of their form. The only difference is that the summation has become an integral, and these values here, they take the index k, and the index h of n minus k takes on only integer values, but no such restriction applies in the continuous time case. Okay, so we have seen how to perform convolution, and given the impulse response of a system, how to use convolution to find the response of the system to any arbitrary input signal. Okay, we have seen both these in this lecture, and in the process you have seen how to perform convolution in the continuous time. Okay, now next what we are going to do is we will be talking about the properties of LTI systems, and while talking about the properties of LTI systems, we will also come across some interesting features of the convolution process itself, and we will highlight what those features are, and that will help us to to identify and get quick information about a system by looking at the impulse response of the system. And also we will come across what happens, or what transformation happens to a signal when we convolve it with certain versions of the unit impulse function. Okay, so we will try to grasp all these concepts in the next lecture, where we will talk about the properties of LTI systems, and also clearly identify and point out what some of the interesting features of the convolution operation itself. Okay, we'll stop here for now, and we will continue in the next lecture.